So without him, we wouldn't have internet and so on. And I believe this. But then I was thinking, okay, so information theory be connected to information geometry. And how is it connected to diffeomorphism? And so this first lecture, I'm going to give my interpretation. And then in the second and the third lecture, we'll do the more geometry part, where I kind of discuss connections. Fluids in particular, and also to optimal. So today will be a bit of kind of origin and motivation. From the point of or perspective of Claude Shannon. Okay, so Claude Shannon called it a mathematical theory of communications. Later it was named information theory. His thinking was something like this. Let's start with some pool of messages. And let's call this pool of messages M. This is a discrete set. Denote the elements by x1 to xm. There's m elements in this. And then you can ask, okay, so if I receive one message from this set, how much information have I gained from that? Okay. Obviously, this must be related to how large the set is. So what is the information content? The information content of one message. And you could say, okay, the simplest choice would be to say I receive one message out of m possible messages. So I have received, the information I receive is m. Okay? If m is large, then I receive a lot of information if I get a message. If m is not so large, I don't receive so much. But actually, and this is, I think this was kind of suggested even before. The idea is that instead you take the logarithm in some basis of m. So the information would be log of m. M is the size. And how can you motivate this? Well, the simplest way is the following. Assume that you are given two messages instead. So then what is the set of possible two messages you can receive? Well, it's just a combinatorial thing, right? So it's m cross m. And you take the size of that would be m squared. So if you take just the size of the set to be your information content, you would kind of, by getting two messages, you would get m squared, have m squared information. But that kind of makes better sense to take the logarithm, because then you get log squared, so you get 2 log. Twice as much information if you get twice as many messages. Kind of makes sense. So this seems to be a good definition of information. There is also a deeper meaning, or perhaps it's not deeper, but there is also kind of another thing which has to do with exactly the strings of messages and how you encode them. So the deeper motivation for choosing logarithms is the following. If you encode your messages in an alphabet where you have a k-letter alphabet, binary alphabet 0 and 1, or it could be our common Roman. You have some K-letter alphabet, and you ask, what is the minimum number of letters I need if I want to represent a message from the set M? Okay, so then that would be exactly log K of M. On average, because it's not necessarily an integer, right? Imagine you draw several messages, and on average, this is how many letters you need. So it makes sense. This is a kind of good first definition of information. But there is one problem here, and I think this is maybe Shannon's first deep insight. There is one problem here. The problem is the following. So when I woke up this morning, I was looking out the window, and it's sunny. And I was surprised, because I don't expect it to be sunny in winter. You know, at least in Sweden, normally it's cloudy. Okay? I was surprised, and perhaps, I don't know exactly how it is in Vienna, but let's assume that it is more common that it's cloudy in winter, okay, than that it is sunny, okay? And somehow, that means if you wake up, you see that it's sunny, you're more surprised. And Shannon thought about it like this. Being more surprised means you have gained more information. You have gained more information. The set has just two. Okay, so what is the set? Set now, M, is the set of sunny, okay, and cloudy, okay, two elements. But with this definition, the information if I see that it's sunny would be just log 2 then, elements. But somehow I feel that I gain more information if I see that it's sunny, because I don't expect it to be sunny. This was Shannon's insight, that he said we have to think about this in a probabilistic sense. We have to say, okay, so what is the probability in Vienna that you wake up in winter and it is sunny, okay? Maybe 1/5 of the days. Have some. So it's more likely that you get this out, okay? 4/5. And then Shannon said the following. Said, typically, when you have messages, not all of them are equally likely. Some are more likely than others. And you receive more information when you get the less likely ones. So he said information is somehow equal to surprise, how surprised we are. And how do you incorporate this? Well, you would then say that the information of being sunny would be minus log of E sunny. That was his definition. Which would be log 5 then. Whereas the information associated with cloudy be log 5/4. Hence the minus sign here, the minus sign, because we want this to be larger. So that's Shannon's first kind of insight, that this is a good we can think of information in terms of this probability distribution of the messages that we receive. And of course, he was, I guess, I don't know, but I suppose he was thinking about text. Because that's the thing, he was working for Bell Labs, wanted to send messages, text messages, let's say, over some channel, and thinking about what is the information, how do I encode this information. And we will see that maybe that this definition is in a way independent on how you encode the information, whereas this first one is not. Also notice that if the two probabilities are the same, is 1/2, 1/2, then this definition of information gives exactly the same one we had here, size of the set. Also, if we say if P of cloudy is 1, okay, what does that mean? Does it mean that P of, so we take log of P, so it's just 0. So we gain 0 information. That's exactly what happens in Gothenburg in the winter when you look up. I don't even have to go to the window. I know it's going to be gray, okay? That's how it is in Sweden in winter. We have exactly this situation. I'm not surprised at all. I gain no information when I look out the window and say, oh, cloudy day. Okay? So this is nice. This is the first step towards in this story. But then, of course, eventually we want to get to what's called the Shannon entropy. Shannon entropy is not exactly this. So how do we get there? That's next insight. So he was always thinking about messages like a string of messages you get from some pool, you know, N. You get these strings of messages. And then he asked the question, well, okay, so if I receive some messages, and I know how likely it is to receive something, so I know this probability distribution. What is from a string of messages, what is the average surprise that I will get? The average surprise. And this is exactly, so average surprise, with surprise or information being then defined like this, is exactly the Shannon entropy. So that's H, so we have to take average. Imagine you draw a lot of samples from this. What is the average surprise? Well, then I have to do this, sum the elements, M, minus sign, and then probability pi times log minus log. This is the first very important formula. And you know probably the story, this formula was not new, it was known in physics, Boltzmann. Statistical physics, the story that you always hear, John von Neumann and what Shannon was discussing, and Shannon showed him this formula and said, I don't know what to call this. Well, you have to call it entropy, first of all, because it's connected to physical entropy. Secondly, no one really knows what it is. If you call it entropy, it will always be the others in a discussion. That's not true at all. He never said anything like that. In fact, Shannon saw himself that this formula has connection. Yes, yeah, that's why I wanted to make the connection. But of course, Shannon knew enough physics to realize that this similar formula appears. Okay, so a few things to notice here with this formula. This is, I mean, many of you, I'm sure many of you have seen this, so, you know. But when I was here 10 years ago, I basically had not done this carefully. So we know this, first of all, it's that this entropy is positive or negative. And that it's zero implies that the probability distribution Pi is equal to some delta I k or some k. So there's a no information. And here is the cool thing. So you can ask, okay, we know when it's zero, we know when it's positive. How do I maximize the entropy? When is it maximized? So what is the distribution that gives me the biggest average surprise? That's exactly when the distribution is even. Okay? So the maximum, max of h, is log m. That's, you remember, our initial so that's one thing I want to say. Yeah. Yeah, because you have to imagine like this. So I draw a lot of samples from this, okay? I get a lot of messages from this. And then, of course, if the probability is higher, I will receive a message more often therefrom. So it has to be a formula like this. Expectation. Yeah, that formula would not. It has to be like this. Okay. So what else do I want to say? So, you know, if you know the distribution of your messages, how common they are, then you can compute the entropy. You can also ask the following question. If I think I know what the distribution is, I think I know that it's going to be sunny, cloudy is going to be distributed like this in Vienna. Maybe it's not true. But then I wake up and I compute all the time. I get my measurements, my samples, and I compute my average surprise. And then I'll see that I was wrong, okay? Because I didn't have the right distribution. I got this distribution, but I didn't have the right values attached to it. Okay? So then I will compute something else. I will compute kind of faulty entropy, if you like. Okay? And that is important because that's often what happens. You think you know the distribution, but you don't exactly know it, okay? And then you get, and there is the first kind of basic inequality is one related to that. And you can imagine, it's kind of intuitive to think like this. If I don't know the distribution the right way, and I get information, then I will be more surprised than if I actually knew what the correct distribution was. And this is a factor, an inequality. So let me state that. So if I think that the distribution is Q1 to QM instead of the correct. And you will see in a while why I want to bring this. Instead of the correct P1 to PM. So then I can compute this by plugging in now my sort of faulty distribution Q1 to QM. And what do I get? I get minus sum I goes from 1 to M pi I pi and then log the QIs instead. And you can check exercise. This is always larger than the proper Shannon entropy. Okay. And if you redo this a little bit, you can see this gives rise to something called, so you take this inequality and you move one over to the other side, you get an inequality, and this is the following one related to relative entropy. So HQ E, which would then be sum pi log pi divided by qi. This thing is always greater than or equal to 0. This is in information theory is called, or information geometry is called a divergence. It kind of measures the measure of the, not really a distance, but some sort of measure of the difference between this distribution and this one. So this will probably, we'll come back to this later on when we discuss the Fisher-Rao metric and its origin and so on. But it also comes up here in an inequality, and this is called, in information theory, they think this is very important, so it's called the information inequality. So all this is very nice. And of course, Shannon developed a nice, rich mathematical theory out of this. But the point of it, why it sort of became so famous, is because it's extremely useful. Extremely useful for thinking about signals. Okay? So another insight of Shannon, and this is called sometimes the first fundamental theorem of Shannon, or of information theory. Is the following. So if h of p is less than its maximum log m, then there should be another encoding which on average uses, instead of using log m bits, we think if we take this in the 2 bases, we think of bits. So it uses h of p bits per message. So this led Shannon to something very important, namely data compression. So the idea is if you have a signal or a message which statistically has this property, we have not found the right way or the perfect way of representing it. The representation we use is redundant. Okay? This is the basis for much of data compression today. Lossless, I should say, lossless data compression. There's also lossy compression. And a good example, and again, this was probably a Shannon's prime example, is to take written text. Written text in our usual alphabet is an extremely redundant way of representing. So if you take text files on the computer encoded in the ASCII encoding, so then each letter contains 1 byte of information. That's 8 bits of information. And if you then look at, and the text, if the text is written in English, okay, and you look at the letter frequency in English, in the English language, by taking a book and just counting how many of each letters you see. So then you get the distribution, and if you compute the entropy with respect to this distribution, you see that the information content is about 4 bits per letter. So we're representing it with 8 bits, but the actual information, if you do it like this, is 4 bits. If you take it even more extreme, because actually, of course, I mean, just looking at the individual letters is not enough. But if you look at words, so you look at sequences of words instead, you think of M, this set, as the set of English words. And then you count the frequency of these words, and you make a corresponding analysis there. Then you see that the average, I didn't compute this, I found it somewhere. So then you see that the average information for each word is about 10 bits. And in English, the average length of a word is 5 letters. So that means the average information per letter is about 2 bits in written English. Much lower than 8 bits. That's how redundant English is. And it's easy to see. Just take some computer, look at all the ASCII codes, and ask it to randomly generate something with a uniform distribution. You get rubbish. You never get anything interesting. Okay? But just by taking letter frequency into account, you see, sometimes it looks like a word. If you take a progression of 2 letters, you get every now and then some English words. If you take 3 letters, it's already a lot better. And you can continue like this. And in essence, this is what you're doing when you're creating these large language models that are so popular today. But you're doing it in an extreme way. So you're not just counting words, you're perhaps even counting sentences and paragraphs and entire books and trying to find the distribution associated with that. Once you have this distribution, you can do conditional sampling. That's what happens when you enter something in bots and you get the replies. Conditional sampling. You specify the first part. Under that condition, what is the most likely outcome? And you get an answer. So, let's see. This is my, perhaps, naive view on what Shannon did. Of course, he did a lot more. I mean, I don't know enough, and I don't have time enough to discuss everything he did. Noisy channels is part of his theory. How do you deal with that? Data compression, as I said, I haven't said anything about it. Part of it. Encryption. I mean, it's a very nice field. Just reading his book. But we should now ask ourselves, okay, so far I haven't said anything about geometry. I talked about information theory. But what about these diffeomorphisms? How do they come into this picture? What about diffeomorphism? So the first thing you have to realize when we talk about diffeomorphisms, we're working with usually manifolds. Manifold has a topology associated with it, some smoothness. So far, you have no topology. Okay, this set M that I was talking about is just a set of elements. So the first thing to kind of make the connection to diffeomorphism, we must ask ourselves, why would it be needed to add some sort of topology on this set of messages? And this is what I think, that a topology is needed to describe noise. Noise attached to the Why is that? Well, if you think about it, you have some message, some element in this set, and then you're saying, okay, I'm sending this message over some noisy channel, copper wire, somehow encoded by. And then it will be exposed to noise. It means there is some chance or risk that the message will actually flip over to some other message. And then you have to say, okay, so which messages will it flip over to? Well, the ones that are close by. You have to have a concept of what close by messages means. Okay? So adding noise to, let's say, a message, X in M, means that we change it to a nearby X tilde. Then, of course, nearby. You could say that whenever you want to introduce noise into this story, you somehow need to have some way of thinking what does it mean for messages to be close to each other. So, for example, if you take 5-letter words, and you define a distance between X and X tilde. X and X tilde are now 5-letter words, as the number of places where they are different. In this string, how many places are they different? So, for example, the distance between the word prime and the word pride would be 1. And this is actually called the Hamming distance. Okay, so maybe at least see vaguely that somehow when we talk about noise, maybe we need to introduce some distance or some topology. We need to know what it means for words to be close. Still, what is the connection to diffeomorphisms? So there are probably many ways of doing this or motivating this. One way could be as follows. So messages are ultimately transmitted by analog channels. Okay. So if we lift the whole story, so one of the great things, the great insights of Claude Shannon was, of course, to make this whole theory of information completely abstract. It doesn't care about what kind of messages you're sending or receiving, or how you're receiving them. I mean, he's not talking about, oh, if I use electrical signal like this with this voltage and this type of copper wire, then I can send this and this much information. That's maybe what many of the engineers at that time, how they were thinking. He took that away and said, okay, let's make a mathematical theory about it. But if you then go back a little bit and think about, in the end, well, assuming that we live in a classical world, we disregard quantum mechanics. The signal is transmitted by some analog channel. I mean, we are reading the voltage. So there is some sort of natural topology on the set of messages from this point of view. Okay? So we take M, motivated by this, we take M as a manifold. Not how it has infinitely many points. Think of this as a kind of continuous signal. And what does it then mean? What does a diffeomorphism mean here? Applying a diffeomorphism to elements in M. Okay? Well, the way I think it means that you're changing the encoding. Because now we represent it in some other ways. We shuffle things around. Okay? So imagine a signal. We're changing how we encode this signal in this analog source, M, or manifold. Okay? But we do it in such a way that nearby messages remain nearby. Okay? So change encoding so that nearby that's one interpretation. Yeah, it's a bit vague now, right? But you have to think of this. Think of when you're sending a text with over a telegraph line with Morse code, for example. That would be one encode. And then you eventually the information is traveling in this electrical signal. The electrical signal is analog. You interpret this as a message. You receive some analog information, you interpret that as a message. So that's the picture that I have in mind. Yeah, so changing the encoding would mean that I'm still using the same apparatus, but I'm changing the way I encode my messages in these electrical signals. So here is this manifold. But in fact, to be quantitative, it's not quite enough with just the manifold. That just says that, that just tells us that what it means to be nearby, but not how nearby or anything like that. At least we need one more thing. Maybe we don't need a full Riemannian structure, but at least I think we need a volume form, a reference volume form. And why do we need that? Volume form, let's call it mu, because measuring volume, the idea is the following. So measuring volume of some little set of messages corresponds to measuring bandwidth, how much information I can store in that little set. So the idea is that volume form corresponds to, or volume on the manifold corresponds to bandwidth. And then again, we need to connect back to what we did before. Then the amount of information that I can store in this system should be correspond to the total volume of my manifold. Okay, so if I had these m messages, then the total volume of m, the manifold now, should be m. This you should think of as the maximum discrete messages that you can transmit in this analog way, given the noise level you have, given this bandwidth, which is so then you see from this that if we now connect back to entropy, of course, now you're thinking, so now I have a message of analog signals. There's when I receive messages from this, there's some probability distribution associated with that. Okay, let's call it rho now. So rho is some probability distribution, let's say smooth on m. And then my entropy would then correspond to minus log, minus integral over m of log rho integrated with respect to mu. And the maximum value, if you think about it, the maximum value is exactly going to be log m. And that's what you get when you take h of the uniform distribution. So it's mu, which is the volume, but that's not that needs to be normalized to be a probability density. You have to divide by m. You compute this, you get exactly. So that's one way of thinking of diffeomorphism in this setting that kind of more or less directly connects to information theory the way Shannon was thinking about it. And now you can ask all sorts of interesting questions like, okay, we have this group of diffeomorphisms, those correspond somehow to encodings, and we can change the encodings. It's natural to define like what it means to be that two encodings are equivalent. What does it mean to encode things equivalent with? Well, those are exactly the volume preserving diffeomorphism. Diff of mu. Equivalent encodings. Why? Well, if you take a diffeomorphism, which is in diff mu, preserving the volume for mu, and you evaluate, and you take some probability distribution associated with one encoding, and then you re-encode it, so that's just applying this diffeomorphism to the probability distribution, then it's a little calculation, which is a change of variables, and using the fact that the volume form is preserved, you see that this is exactly just h of rho. In that sense, it has the same entropy, so I haven't changed anything. It's an equivalent encoding. But the point is that you can get non-equivalent encodings by applying the whole group of diffeomorphisms. So in a way, you can say that if you represent your signal like this analog way, and you compute for some pool of messages, some source of messages, you compute the probability distribution, or you get the probability distribution, and then you compute the entropy, and you see that the entropy is not the maximal one. It means that you're not using your sources, your communication sources are not used optimally. So from this point of view, to connect to physics, what is the heat flow trying to do? The heat flow is trying to reach the optimal kind of encoding. That's one way of thinking of it. Yeah. Let me change the... I have a little spot here, so maybe... I don't have much time left, I think, so I'll try to finish. Because I want to eventually say something about that connect. So I've been saying something about diffeomorphisms, right, now, and maybe about information theory, but geometry also. How does geometry come into play here then? Maybe just something about that. Well, so the first basic question then in information geometry would then be the following. So assume that you have this device, this analog device for sending messages, and then you use it for two different sources of messages. Okay? So these two different sources of messages will have correspond to two different probability distributions. So you have two sources corresponding to rho naught and rho 1, both in the space of probability distributions on M. And then it's natural to ask now also not just what is the, what does it mean for messages to be nearby, but what does it mean? What does it kind of mean for these two distributions to be nearby? Okay? So that's what gives us leads us to geometry. And once you do this, you think, okay, so this is the source. This has something to do with the information, that I want to convey. So it should not depend on how I encode the information. Okay? So the distance, so somehow I want the distance, I want to define the distance between rho naught and rho 1 so that it's independent of encoding. And coming back to what we said about diffeomorphism, this means it should be independent of, it should have this invariance that if I apply some diffeomorphism to both of them, so I change the encoding, then I should get the same thing. So that's the first thing that we want. And this, I think, is very reasonable thing to say if you want to disconnect this distance to the way that we actually encode the message. So the next thing that we want this distance to be Riemannian. Why do we want this? Well, Riemannian is nice. I don't know. I don't have a very good motivation for that. Okay? But maybe it is natural to look at a Riemannian distance. Okay? And then the third one, what do we want? Well, this is not what we want. This is what we absolutely wish for. What if there's actually a unique distance? Then that would be great, right? And in fact, if you say that it's Riemannian, it is unique. So the last thing we want is it should be, or we want it to be unique. And this, of course, leads us to the Fisher-Rao metric. That metric interacts with these diffeomorphisms. And the story that I'm going to tell you from tomorrow, last bit of board left here, is to show how this Fisher-Rao metric, which comes up in information geometry, how sort of these fields, information geometry, which is, if you like, is about Riemannian geometry of statistics, or if you take this point of view, Riemannian geometry of information theory, how that is connected to Riemannian geometry of diffeomorphisms, which is normally called geometric hydrodynamics. So to get kind of this connection. And then the last field that is also connected here is what sometimes is called autocalculus. If you like, you can think of that as Riemannian geometry of optimal transport. And these three fields interact in a very beautiful way, and that will be